Welcome back to this lecture on set operations. In this fourth segment, we will introduce the concept of a membership table, which applies to any number of sets from 2 up. Let's give an example with 3 sets. So let R, S, and T be any 3 sets. To build the membership table, we're going to write each one of these sets at the top of its own column. Now, consider any element X of the domain or the universe. What are the possibilities for X belonging to any one of those 3 sets? Well, the first possibility is that X belongs to the universe, but it does not belong to any of the sets R, S, and T. We're going to indicate this by 3 zeros. In other words, a 0 means that the element X does not belong to the set corresponding to the column. So this 0 means that X does not belong to R, X does not belong to S, and S does not belong to T. So if you remember the picture of a Venn diagram with 3 sets, this would be the situation where the element is inside the universe but outside of those 3 sets, those 3 circles. Now, of course, it's possible that if you take any random element of the universe, it could belong to exactly one of these sets. For example, it could belong to the set T. And we would indicate this with 0 since it doesn't belong to R, 0 since it doesn't belong to S, and a 1 since it belongs to T. Or the random element of the universe could belong to only S, which we would indicate with this series of 3 entries. Of course, a random element could belong to both S and T, but not R, which we would indicate like this. And I think you can see the pattern developing. Every row corresponds to one possibility of a random element of the universe belonging to a combination of the sets R, S, and T. And by choosing 0 to mean that X does not belong to a set and 1 to mean that X does belong to a set, we're basically building a 3-digit binary number. So the next combination would be that X belongs to R but not S and T, and so on and so forth. And these are all the possibilities for the membership of a random element X of the universe, from belonging to none of the sets to belonging to all 3 of them, and everything in between. So now we can actually ask the question, take a random element X of the universe. Does it belong to S union T? So the membership table will allow us to demonstrate the properties of union and intersection, for example. So now let's go through every possibility, every one of these 8 cases, and determine whether S or X belongs to S union T. In other words, we're going to look at those 2 columns, the column for S and the column for T. So for example, here X does not belong to S and it does not belong to T. So therefore it does not belong to their union. On the other hand, since here X belongs to T but not to S, it does belong to the union. On the next row, X belongs to S, so it clearly belongs to the union of the 2. And here, X belongs to both of them, so it clearly belongs to their union. And so on and so forth, all the way down the columns. Let's do the same thing for now the set R intersect with S union T. So now we're looking at this first column for R and this column for S union T that we just built. When does a random element of the universe belong to R intersect with S union T? Well, whenever it belongs to both R and it belongs to S union T. So every time we have a 1 in this column and that column. Since we have a 0 on the first 4 rows here, we're going to have a 0 in the intersection. And since we have a 1 here in the first column, whether X belongs to the intersection will be determined by whether X belongs to the second operand of the intersection. In other words, this column here will be copied in the last column. So this is basically a membership table that determines the membership in this set and that set based on the membership of a random element in the three original sets. So to make clear that this is a table, a two-dimensional table, let's put the lines for the rows and the columns. And now we're going to actually use this membership table to prove this equality that we discussed in the previous segment. Now, the main advantage of a membership table over a Venn diagram is that if you build the membership table correctly, as we did, it covers every possible case of membership in the universe. For example, in a Venn diagram, if you don't draw the circles intersecting each other pairwise, you won't get all of these 8 possibilities. So that's why a Venn diagram in general is not a valid proof technique. But on the other hand, a membership table is a valid proof technique, and I'm going to demonstrate this here by proving this set identity, which is basically one of the distributivity identities that we discussed in the previous segment. Notice we already built the membership table for the left-hand side of this identity right here. So now what we need to do is to build the membership table for the right-hand side. We're going to start by building a column for the intersection of R and S, which means we're going to look at the first 2 columns, and a random element of the universe will belong to their intersection only when it belongs to both R and S, meaning when there's a 1 in both of the first 2 columns. And that only happens in the last 2 rows, here and here. Now, let's build the membership table for the second operand of the union, namely R intersect T. So now we're going to look at the first column and the third column, and we're going to put a 1 in this column only when we find a 1 both in the first and the third column. And it happens on this row and on this row only. So here is the membership table for R intersect T. And of course now we're ready to build the membership table for the union of this set and that set, which is the union of these 2 sets. So in the column, in the membership table for the union, we have a 1 exactly when there's at least 1 on the corresponding row for the 2 columns. And so this is the complete membership table column for the right-hand side of the equality. And because the membership table covers every possibility of any element of the universe belonging to the sets R, S, and T, we can prove that these sets are indeed equal, this set and this set, simply by checking that a random element of the universe always belongs to both sets or always belongs to neither one of them, simply by checking that the column for one set is identical to the column for the other set in the membership table. And that is the usefulness of a membership table. Because it is systematic, it is a valid proof technique, as opposed to a Venn diagram, which, depending on how you draw the circles again, you may not consider all possible cases. And the other advantage of a membership table is that even if you have 4, 5, or 6 sets, you can always increase the size of the membership table by adding rows, and you can still prove the identity you're interested in. Whereas with a Venn diagram, I let you imagine how hard it is to draw a Venn diagram for 4 or 5 sets and trying to represent all the possible combinations of intersections among them. So this concludes our discussion of membership table.